Gay-Lussac's law. Here's a tanker car, and when they're empty, they can be cleaned out using steam. So you can climb down in there and you can spray out the inside with basically hot water and steam. What could happen is after they've been cleaned out, they're really hot. So all the particles of gas that are inside them, imagine it's just gas, they drain out of the liquid. All the particles have a lot of kinetic energy, so they're moving around with a lot of energy. If you close the lid on your way out, these particles are going to be stuck in here. No particles can come or go, so it's just the ones that are in there. And initially they'll have lots of energy. But as they cool down, they're going to end up with less energy. So they're pushing on the outsides of the tanker car here. And outside the tanker car, there's a whole bunch more of less energetic, but much more of them, particles from the atmosphere pushing on the tanker car. So there's ones on the inside pushing out, ones on the outside pushing in. As long as the ones on the inside have lots of energy, they can counteract all of the ones on the outside. But as these guys in here lose their energy, they have less energy to push back on the atmosphere's pressure outside. And what can happen is the atmosphere can actually crush the entire tanker car just because of the pressure exerted by the gas particles in the atmosphere being greater than the pressure of the particles inside the tanker car because they've lost all of their energy. Gay-Lussac saw this relationship between pressure and temperature, and essentially what he saw is that if you have temperature going up for a particular sample of gas, then the pressure of the particles in that gas would also go up. If the temperature goes down, the pressure will go down. So this is a proportional relationship again. And we know we can express proportional relationships like so, where the initial pressure divided by the initial volume will be the same as the final pressure divided by the final temperature. Like I said, volume there. Initial pressure divided by initial temperature equals the final pressure divided by the final temperature. But remember, the temperature has to be in Kelvin. We don't want to have to cross the zero scale and be dealing with negatives because we'll lose our proportional relationship. So always convert temperature into Kelvin. So let's try this out. If we had a can of gas and it had a pressure of 101.3 kPa when it was at 25 degrees Celsius, what would the pressure be if you heated it up to 100 degrees Celsius? And we know from the warning labels on these aerosol cans, this is not something you should be doing, because as Gay-Lussac described, as you increase the temperature, the pressure inside the can's going to change. And if it gets too high, it won't implode, it'll explode. So we're going to use Gay-Lussac's law to calculate what this change in pressure will be. We're solving for the final pressure, so we want that variable isolated. We've got to get rid of this final temperature. So if we multiply both sides by final temperature, it'll cancel out from the right hand side of the equation, because the numerator and the denominator both have the same term in them, so they're gone, and it'll give us an equation for final pressure. So final pressure will equal the initial temperature times the final initial pressure times the final temperature divided by the initial temperature. Then it's just a matter of taking your variables from the given information, plugging them into the equation. Remember that your Celsius temperature values have to be converted to Kelvin. So you do that by adding, and you go from Celsius to Kelvin, you add 273. So this, for example, would be 373 Kelvin. We don't say degrees Kelvin, we just say Kelvin. 25 degrees Celsius, you add 273 to that, and you're going to have your 298 degrees Kelvin. So plug those values in and make sure you're getting the right one in the right place. We know that Kelvin are going to cancel out, and so this will give us our value in kPa, and we'll end up with a final pressure of 126.8 kPa.